Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and today we'll be doing unit number 5, lesson number 11 on translations in the coordinate plane. Alright, so for the last couple lessons what we've been doing is we've been revisiting the transformations, specifically rigid body motions, that we saw back in unit number 2. And so far we've looked at rotations in the coordinate plane, and we've looked at reflections in the coordinate plane, both of which are going to pop their heads up in today's lesson. So if you haven't actually kind of reviewed those or studied them yet, this lesson could be a little bit problematic, all right? So if you're just looking at a lesson on translations and you haven't looked at the other two, this may not be the lesson for you, all right? But let's jump right into them because translations in the coordinate plane are relatively easy. All right, especially just relatively easy to pull off compared to reflections and rotations. Let's take a look at exercise number 1. All right, in the diagram shown below, AB is drawn with endpoints at A, -2, -8, and B, 7, 4. It says draw the image of AB after a translation by 5 units left and 3 units up. So we're going to shift this thing 5 units left and 3 units up. Label its image A', B', and give the coordinates below. As usual, I have forgotten a ruler, so I'm going to go grab it. All right, back to here. Okay, just so I can draw that straight line segment. Okay, let's do it. We need to translate 5 units left and 3 units up. Let's do that together with point A and see if we can see a little bit of arithmetic that will help us do translations a lot quicker. So if I take A, and I move it 5 units to the left, and I move it 3 units up, right, then A prime is sitting at -7, -5, all right? Now, we can certainly do that graphically, and there's no problem with doing it graphically. But what's nice about translations in the coordinate plane is you can really just do them with adding and subtracting, where shifts to the left and down represent subtraction, and shifts to the right and up represent addition, or vice versa. All right, here's what I mean. You know, I could have, without a coordinate plane, said, well, I'm going to shift it 5 units to the left, which means I need to subtract 5 from the x-coordinate on A. Likewise, if I'm going to shift it 3 units up, I could take that y-coordinate and just add 3. So instead of doing it graphically, I can simply subtract 5 from the -2 and get -7, and I can add 3 to the -8 and get -5. Why don't you do that and come up with the image for B? All right, well, let's take a look and then kind of verify that this works. Right, B prime, I'm going to take that 7 and I'm going to subtract 5 in order to move it 5 units left. And then I'm going to take that 4 and I'm going to add 3 to shift it 3 units up. And I'll find that B prime is at 2, 7, right here. And again, just to verify what we saw, if we actually now track it, it is definitely 5 units this way and 3 units that way. My last little piece is just to connect those two using a line segment, so why don't we do that? I'll go back and label A prime in just a minute. And there is my line segment. Okay, label my A prime. So we've got line segment AB and line segment A prime, B prime. Now, again, what we want to do is we want to also bring in the tools of coordinate geometry to verify properties of rigid bodies that we've seen before. And let's take a look at the length of AB and the length of A prime, B prime by using the distance formula. Okay? So let me work through the length of AB and then have you work through the length of A prime, B prime. All right, let me just scroll up a little bit here. As always, the distance formula is just the Pythagorean theorem, right? x2 minus x1 squared, y2 minus y1 squared. I squared two things, add them together, take the square root. So let's do it. For AB then, that's going to be 7 minus -2 squared plus 4 minus -8. Ooh. That negative didn't come out very well there. Let me try to put it in there a bit better. All right. 7 minus negative 2 is 9 squared, plus 4 minus negative 8 is 12 squared. That's going to give me 81 plus 144. All right, and that gives me the square root of 225. I'm taking up absolutely all the space I'm going to have for a prime, b prime. 225 is a nice perfect square. Its square root is 15. So the length of segment AB is 15 units long. What I'd like you to do now is use the distance formula to calculate the distance between A prime and B prime. Between A prime and B prime. Go ahead and do that. All right, let's go through it. Now hopefully what you found was that they were the same. All right, let me kind of section this off a little bit. Maybe go in red to give ourselves a little bit of contrast. Here's my A prime. Here's my B prime. So the length of that will be the square root of 2 minus negative 7 squared plus 7 minus negative 5 squared, all under the square root, of course. 2 minus negative 7 is 9 squared. 7 minus negative 5 is 12 squared. Again, giving us the square root of 81 plus 144, which is the square root of 225, which is yet again 15. All right. And of course, this is exactly as it should be. A translation is a rigid body motion, and one of the many properties of rigid body motions is that they preserve length. They preserve distance. That line segment can't change its length under a translation. But translations, as a rigid body motion, also have one more interesting property that most rigid body motions don't have. So let's take a look at that right now. Letter C asks us to calculate the slope of AB and the slope of A prime B prime, and then compare and talk about what that means. Let me write down the coordinates of the points right now. So we've got point A, which is at negative 2, negative 8. Point B, which is at 7, 4. A prime, which is at negative 7, negative 5. And B prime, which is at 2, 7. Now, you should be very, very comfortable with the slope formula at this point. All right, so what I'd like you to do is pause the video now, calculate the slope of AB, calculate the slope of A prime, B prime, compare the two, and tell me what that tells you about the two segments. All right, let's go through it. Slope, y2 minus y1 divided by x2 minus x1. All right, for AB, that's going to be 4 minus negative 8 in the numerator and 7 minus negative 2 in the denominator. 4 minus negative 8 is positive 12. 7 minus negative 2 is positive 9. Always reduce your slopes. Both of those can be divided by 3. So AB has a slope of 4/3. Let's take a look at A prime, B prime. For that, we're going to have 7 minus negative 5 in the numerator and 2 minus negative 7 in the denominator. 7 minus negative 5 is positive 12. 2 minus negative 7 is positive 9, reducing, and we get 4/3. So the fact that the slope of AB is 4/3 and the slope of A prime, B prime is 4/3, what does it tell you about the two line segments? Well, it tells you that they're parallel. So in other words, AB is parallel to A prime, B prime. Now again, that is not true of all rigid body motions. If I take a line segment and I rotate it by 90 degrees, its image will not be parallel to the original line segment. But for translations, every translation that isn't in the direction of the line segment itself, every translation will then produce a line which is parallel to the original one. And that is definitely a property of translations that you're expected to know. all right? And it's pretty obvious just visually speaking, right? It's pretty obvious that this line segment and this line segment are parallel to one another, okay? Anyway, let me step out of the way. There's a lot on this screen, so take a moment to kind of copy down anything you need to here. I'll raise the screen a little bit, give you a little bit more time with the slopes, and then we'll move on. All right, bottom portion of the screen. Okay, let's take a look at some more problems. Now, translations in the coordinate plane are so easy because either mechanically you're adding and subtracting from the x and the y coordinate, or graphically you're literally just saying, well, if I take that point and I move it 3 units to the left and 1 unit right, or actually from your perspective 3 units to the right and then like 4 units up or something, well that's very, very easy to do. So we're not going to do any more of those per se, but we're going to try to kind of bring them all together now with some of the other transformations. So let's take a look at a very typical multiple choice problem. All right. Exercise number 2. In the diagram shown, kite ABCD has undergone 2 transformations. Which sequence of transformations, it should say transformations, maps ABCD onto A prime, B prime, C prime, D prime, and then onto A double prime, B double prime, C double prime, D double prime. Ooh, that is a mouthful. All right, so which of these get the job done? So what I'd like you to do is take a moment and kind of walk through each one of those and see if one or more of them strike you as more reasonable than the others, and then we'll talk about each. All right, let's go through them. So the first thing it said is a reflection followed by a rotation. All right, well, if I have this kite, right, and I reflect it across the y-axis, it would end up, kind of being over here. Reflected across the x-axis, it would be up here, but then all the letters would kind of be reversed and the shape of the kite would be reversed. So it most certainly isn't number 1. So number 2, a translation. Well, let's see. If I took this and I just shifted it up to here, yeah, that would work, right? When I'm doing a translation, okay, nothing really changes sort of the relative location of the letters on the figure, right? And everything kind of stays parallel. That would be parallel to that, that stays parallel to that, that kind of stays parallel to that line segment. So it does seem very reasonable that a translation would be the first one. Now that would be either then choice 2 or choice 3. The question is, after doing this translation that kind of maps this to this, did I then follow it by rotating, or did I follow by reflection, right? Now both of them seem like it could be the case. If it was a rotation, maybe there'd be some kind of like point down here that I rotated it 90 degrees around. And if it was a reflection, maybe it's, some kind of reflection across that line. So how can I distinguish? And actually the symmetry of the kite figure itself makes it nearly impossible to do so. What really tells me that it's one versus the other is how the letters play out on these 2 figures. You see, if it was a rotation, if I was taking this kite and rotating it down here, then A prime would go to A double prime here, B prime would go to B double prime here, D prime would go to D double prime here, and C prime would go to C double prime here. Now A prime, that's good, C prime, yes, but the D prime should have landed down here if it was a rotation, but it didn't. It ended up here, right? Which actually means it's a reflection. And it's probably a reflection in the line y equals x, right? So what happened was I flipped A prime over that line and landed on A double prime. D prime landed on D double prime here. B prime reflected down to B double prime, etc. So this is in fact choice 3. And if that's the one that you chose, then you've got a good feeling now for how these things can kind of combine with one another. Again, it's all about where those kind of letters ended up being. If there were no letters on these figures, well, number 1, it would be hard to know which one came first, which one came second. But if there weren't any letters, and we knew this was first, second, and third, there really would be no way, because of the symmetry of the kite, to distinguish between whether a translation was followed by a rotation or a reflection. But again, because of the way these letters are oriented, and they're kind of oriented in the opposite direction, right? A, B, C, D, I'm kind of going around here in a clockwise way versus A, B, C, D. Here I'm going counterclockwise. Whenever you reflect a figure, its orientation changes, meaning that like the letters will go in the opposite direction that they did before, clockwise, counterclockwise. That only happens with reflections. All right, let's take another one. Okay. This is a very standard thing you're asked to do, and we did some of this back in Unit 2, which is to come up with sequences of transformations that will map one figure onto another one. Let's take a look at exercise 3. Give two different sequences of transformations that show that parallelogram ABCD is congruent to parallelogram EFGH. Be as specific as possible about your transformations. Okay, so I want these sequences, and this is something where it is very, very helpful, very helpful to be able to use tracing paper. All right, so here I've got my prefab tracing paper, right? My red parallelogram that I can just lie on top of ABCD. I would suggest now for you to take out a piece of tracing paper, carefully trace over this parallelogram, and then think about a sequence of just two. You should need just two transformations to get this parallelogram to fall on top of that one. Why don't you go ahead and do so? All right, let's go through it. Okay, so many different ones that would work. All right, one of them that would work is basically taking this, translating it up so point C gets translated to point E. So I'm going to do this. I'm going to do a translation that moves or maps point C to E. All right? And that would put us right there. Now I'd like this thing to land on top of that. Now how will I do that? Well, I would do it by doing a reflection across some vertical line. Which vertical line though, right? If I reflect it across this vertical line, right? And let me do that. For me, I have to use what's called the flip command. All right. If I reflect it across that vertical line, then all the vertices map on top of each other. And what vertical line is that? Well, that is the vertical line x equals 2. Remember, vertical lines will have equations x equals, horizontal lines will have equations y equals a number. Okay? So that's one set of transformations that would work. Let me get this thing back to where it was before. Okay. So let's take a look at another set. All right. Now, another way to do it, okay, and again, there are many different ways, but another way to do it would be to take point B and map it up to point H using a translation. Something like that. So maybe a translation, and I'll use the word maps this time. Maps, what was that? B to H. All right. But now, if I want the red parallelogram to fall on that, I've got to reflect it, right, in this direction. Now, what's cool about that is that you could say at this point, just reflect it across HG. You could do that. But since we've been working with horizontal and vertical lines lately, what is that line? I'd want to reflect it across this line. And that's the line y equals 3. And when I do that, let's take a look at what happens. Flip, up, down. It then lands where I want it to again. So reflect across y equals 3. All right. In either case, what happens is that we end up getting all the vertices of A, B, C, D to fall on top of all the vertices of E, F, G, H, or E, F, G, H. Yeah, E, F, G, H. And therefore, the two must be congruent. All right? Let me step out of the way, write down anything you need to, and then we'll move on to another exercise. All right, let's do it. Take a look at what we've got here. Another one of these kind of multiple transformation problems. Exercise number 4. In the diagram shown, triangle EFG can be mapped onto triangle MNP by a sequence of transformations. If the first one is a clockwise rotation by 90 degrees about the origin, then what must be the second transformation? Describe it in as much detail as possible. Okay, so I'm mapping this thing on top of that thing. And I'm saying there's going to be two transformations. The first one will take this and rotate it 90 degrees clockwise about the origin, and then it must be followed up by one other transformation to get it to map on top of this right triangle down here. What is that transformation? What I'd like you to do is play around with this problem a bit. Okay, let's go through it. Well, to me, the logical thing to do is to actually draw the image of EFG after it's had that 90-degree rotation. Now again, remember, an easy way to do 90-degree rotations is to do a 90-degree rotation. In other words, I'm going to go like this, right? Clockwise rotation. And what that tells me is that if I use the standard notation, that E prime will end up being at 3, 4, right? F prime will be at 3, 1, and G prime will be at 9, 1. All right, now what I'm going to do is rotate it back. Whoops, let's try to rotate it all the way back and plot E prime, F prime, G prime. So I've got 3, 4. Let's see, that would be, might as well label it E prime, 3, 1. That would be F prime, and 9, 1. That would be G prime, giving me that right triangle. There we go. There's my image after that first transformation. Now, how do I get this one to fall on that one in a single transformation? What would that be? Well, I can do it with a reflection. Unfortunately, it won't be a reflection across the line, across the x-axis. That would put me a little bit short, right? Kind of like this. It's definitely a reflection over a horizontal line. I hope you can see that. And the way you can really figure out what horizontal line it will be, let me go to blue, is by doing this. Take this point and connect it to this point. And maybe this point with this point. Okay? So whatever the line of reflection is, it's got to be perpendicular to those two blue segments, and it has to bisect them. Well, these are 1, 2, 3, 4, 5, 6 units apart, and therefore the line of reflection must go through those midpoints, in which case it would have to be a reflection in the line y equals -2. And that is truly as much detail as we need. I mean, I'm telling what kind of transformation is. It's a reflection, and specifically in what line? Oops, it's y equals -2. My mistake. In the line y equals -2. All right, it's kind of cool though, because you've got to know how to do that rotation by 90 degrees. Now, if you botched it and maybe did a rotation by 90 degrees in the counterclockwise direction, then it would then be followed up by a different type of reflection. But if you had shown the original image of your rotation and then got the correct reflection based on that, well, then that still shows a lot of good knowledge in terms of reflections. All right, let's take a look at another problem, the last one. Now, beware, sometimes multiple choice problems can be beasts, and this is one. So let's take a look at it. Exercise number 5. Which sequence of transformations below could be used to map triangle ABC onto triangle WXY? And then there are some very technical transformations. We've got rotations by 90, reflections across the y-axis, reflections across things like y equals 1, y equals negative x, y equals x. So how do you do something like this? And really, you kind of have to go through each one of the choices and see what happens. The question is, do I really have to go through each one of the choices with all 3 points on triangle ABC? And there the answer is no, okay? And let me show you why. Let's take a look at the first choice with point A, okay? So point A has coordinates 2, 8, all right? Let's see where that thing goes after we do a clockwise rotation by 90 degrees, followed by a reflection across the y-axis, all right? So I'm going to get rid of that. We know which point we're rotating. We're going to do a clockwise rotation by 90, okay? And then we're going to reflect it across the y-axis, which this is the y-axis now. So it would put us right here. It would put us at negative 8, negative 2, all right? The thing is, let me get rid of that, oops. The thing is, negative 8, negative 2 is right here, and that's not one of the 3 vertices of WXY. So if A, after that particular transformation, doesn't end up being right on one of those 3, well, then it's not the right transformation. Now, if it does fall on one of the 3, it doesn't necessarily mean it's the correct transformation. We could have just gotten unlucky, but this definitely means it's the wrong one. So let's do exactly the same thing, but try, there we go, try number 2. Number 2 says a counterclockwise rotation by 90, counterclockwise now, followed by a reflection across the line y equals 1. Well, again, let's take a look at what happens with point A. Let's take this and let's do a counterclockwise rotation by 90, okay? And now I have to reflect it across the line y equals 1. And this is where it's essential for you to say, all right, well, I know y equals 1 is a horizontal line like that, and if I reflect across that line, I'd have to be on that point. And what is that point? That's the point negative 8, 0. All right? Now I'm going to, I guess, move this down here. That's convenient. Rotate this back up. And again, the point negative 8, 0 is right there. It's simply not either WX nor Y. So that choice is out. We're just kind of eliminating them based on a single point, based simply on point A. Okay. Let's try choice 3. Choice 3 says a reflection over the line y equals negative x, followed by a translation of 2 units to the right and 3 units up. This one I think I'm going to attempt to do without kind of moving around on my grid. So first, a reflection across y equals negative x. Well, if you saw our video on reflections, or if you went through a separate one with your teacher, then you should have learned that when you reflect across the line y equals negative x, the two coordinates x and y both switch and they negate. So you end up having the point negative 8, negative 2. But then if I translate 2 units to the right, that means I'll be at negative 6, and 3 units up, that means I'll be at positive 1. Well, where's negative 6, 1? Well, negative 6, 1 ends up being right here, right on top of W. Now, it doesn't necessarily mean this is the correct one, but for the first time at least, point A has gotten mapped to one of the points on this image triangle. Let's try point B. All right, Point B is at 2, 4. So let's do that one. Under the same transformation, I'm going to reflect it in y equals negative x, which is going to switch and negate the 2. Negative 4, negative 2. Then I'm going to shift it 2 to the right, which means that negative 4 is going to become negative 2. And 3 units up, that means that negative 2 is going to be positive 1. And that's right there. This is looking pretty good. Why don't you go ahead and try the last vertex, point C, and see if that transformation gets the job done. It does, but let's take a look at it. So C starts at the point 8, 6. Again, after a reflection in y equals negative x, that becomes negative 6, negative 8. When I then translate it 2 to the right, that would be negative 4, and 3 up, that would be negative 5, and negative 4, negative 5 puts me right there. All right, so A mapped to W, B mapped to X, and C mapped to Y, and we've got choice 3. What we would find is if we went through choice 4, again, it would fail to map to any one of the 3 vertices, letter A, so we would know we were right. All right, let me kind of step out of the way, have you think about this for a moment, then we'll wrap it up. Okay, let's do it. So transformations in the coordinate plane, like rotations, reflections, and translations, right? They can oftentimes have rules associated with them. Certainly when computer programmers put this into image processing programs, right? When they have to tell a program to translate an image, to move it, or to rotate it on a screen, or to reflect it across. These are all things that you can oftentimes do with filters and other things on your phones, right? Those things have to have mathematical laws that govern them because there isn't somebody inside of your phone who's sort of like manipulating it themselves. There's got to be computer programming that basically puts these rules into that coding and allows images to be manipulated. And again, the beautiful thing is when you have a picture and you have all of these extremely tiny pixels, each one of those can be given a coordinate point and then be manipulated with these various rules. All right. Sometimes the rules are worth memorizing, in my opinion, like reflections across y and x, y equals x, y equals negative x, or let's say translating by adding and subtracting to the x and y coordinates. And sometimes they're not so worth memorizing, like with the rotations. All right. That's something, though, that you've got to find out for yourself in terms of what you want to do, where you want to put your time in terms of studying and working on the math. For now, though, let me just thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.